Hi everybody and welcome to my channel and this video on the reactivity series of metals. Now before I start, can I just remind you and ask you if you can please go and click the subscribe button at any point during this video just underneath and leave a like and a comment. If you've got any questions or any comments at all, just leave those in the box below. It does make it worthwhile, does help me make some more of these videos. So we're looking today at the reactivity series of metals, which is from topic 4, chemical changes, and it's part 1, reactivity of metals, and I'm going to do it as lesson 1. And what we're going to learn about today is the order of the reactivity of metals, the evidence we use to make this reactivity series, why we put carbon and hydrogen in the reactivity series of metals, seeing as they are not metals. Carbon is obviously a solid non-metal and hydrogen's a non-metal gas. And then we're going to look at the reaction of some metals with oxygen, acids and water. In fact, we might not do oxygen today. Okay, so reactivity of metals. Metals all react in similar ways. Some metals are more reactive than others. And we can put these metals in a series based on their reactivity. And this is useful because we can use it to make predictions. And the reactivity of the metals is based on how easy it is to form a positive ion. That's kind of the technical description. Okay, so metals, when they react, generally form positive ions, and how easy a metal finds it to do that gives it its reactivity. So the easier it finds it to make a positive ion, the more reactive the metal. So for example, you will probably have seen potassium being put into water and it's very reactive, and that's because potassium finds it very easy to form a positive ion. And this is the reactivity series as you would be expected to know it for the AQA exam. So starting at the top we have our most reactive metals, at the bottom we have our least reactive, and then we've got carbon and hydrogen in bold because they are the non-metals, and there's a reason why they're in there and we're going to have a look at that later. So the order is potassium, group 1, sodium, group 1, lithium, group 1, so the top 3 are all group 1 metals. Then we get calcium and magnesium from group 2. Then we get carbon. Zinc, iron and copper and gold are all transition metals. Okay, gold is the least reactive one. It's the only one of these that is found what we describe as native. Okay, and that means we find it as elemental gold. You can find a lump of gold in nature just lying around in a stream, buried in a side of a mountain underground. You can find a lump of gold as pure gold, but you can't find any of these as the pure metal, unless obviously somebody has made it and then thrown it away. So you need to know this series. You are expected to be able to know this series and refer to it and make predictions from it for your exam. So we're going to have a look at the experimental evidence. How do we know that order of reactivity exists? Okay, so number 1, we can do it in a school lab by using water. Nice and simple. Some metals, like the alkali metals we talked about there, your potassiums, your lithiums, your sodiums, and also calcium, react quite violently with water. There's a lot of fizzing, there's a lot of heat given off, and in the case of potassium it even bursts into flames. And we can measure how much the metals react in 2 ways. One, we can do it subjectively by watching how vigorous the reaction is, in other words how much it fizzes. Or we can do it objectively by measuring the temperature change over time. I should say over time. The more reactive, the greater the temperature change. Now, subjective means it's your opinion. Objective means it's a fact that it's out there. So measuring the temperature is something that you've got facts, you've got numbers and evidence to back it up. Subjective is just you saying, I think this one bubbles more. Now, what you might see is that the alkali metals and calcium certainly bubble a lot. And then you might see the magnesium, also group 2, has tiny little bubbles. But the problem is, with just using water, is things like zinc and iron, you won't see anything when you put them into water. Okay, they do react, but the reaction is so slow that we can't see it in a lesson. Okay, even over several days. Obviously we know iron will eventually rust when it's added to water. Now the solution, what can we do for this? Is we can react them with acids. And again, we can measure the reactivity in exactly the same way as we did with water by looking at how much it fizzes or how much the temperature changes. And we will see now that zinc and iron will react with the acids and to differing degrees, but the copper won't. Okay, Copper won't, especially not with cold or dilute acid. However, we will never do the alkali metals in acids because the reactions can be dangerously explosive, which is why it's a good idea to use a combination of both acid and water to test the reactivity of the metals. We can't use if the alkali metals just explode as soon as we put them in the water, it's very hard to measure which one reacts the acid. It's very hard to tell which is the most reactive if they explode straight away, and likewise it's very hard to see for water and zinc and iron which is the most reactive out of those two, because the reaction is very similar. So this is why we need to do both of these types of reaction. So we're going to look at what happens now when we react metal with water. So when a metal reacts with water, it's going to make something called a metal hydroxide, and it's also going to make hydrogen gas, which is what we see is the bubbles. All hydroxides, by the way, when we look at their chemical formulas, contain OH joined together. And the OH has actually got a little minus charge on it, which you can see over here, a minus charge, okay, because it's got a single negative charge on it, a -1 charge. The metal hydroxide compound, the overall molecule of the metal hydroxide, must be a neutral charge overall, and so the charge on the metal must balance the charges on the OH or the OHs, and we'll have a look at that now when we look at the group 1 metals with water. So for any group 1 metal with water, what we get is metal plus water makes metal hydroxide plus hydrogen. Here is an example for potassium. We get potassium plus water makes potassium hydroxide plus hydrogen. You can do this for any metal that reacts with water. It's the same thing here. All you have to do though is swap the potassium in both of these cases for the name of the metal you're looking at. So that might be lithium, it might be sodium, it might be magnesium if you're going for group 2, it might be iron if you're going for a transition metal. And it's exactly the same. Iron plus water makes iron hydroxide plus hydrogen, for example. Now this is a symbol equation for it. Potassium is K, and it's solid. 2 lots of that react with 2 lots of water, which is a liquid, to make 2 lots of our potassium hydroxide. Here we got our K for our potassium, and our hydroxide is the OH, and that's aqueous because it dissolves in water, and we make our hydrogen gas. All of the group 1 metals, and indeed any metal that's got a +1 charge, will follow the same pattern where you can just swap the potassium out for, say, lithium and have 2 Li plus 2 H2O makes 2 LiOH plus H2, just like we've got here. Cs for cesium, Rb for rubidium, etc., etc. Now, group 2 metals in water. This time, the group 2 metals, as you should know from topic 2, they have a charge of +2 when they react. When they form an ion, they have a charge of +2. So you're going to need 2 hydroxides, with each with a -1 charge, to balance out this +2 charge, to get it to be neutral, to be neutral and have 0 charge altogether. The word equation is still the same, as I said earlier. Calcium plus water makes calcium hydroxide plus hydrogen. But the symbol equation is slightly different. Similar, but different. Starts off the same. We get calcium, solid, but only one of them this time, plus 2 waters, liquid, makes calcium hydroxide. So we've got Ca and then in brackets OH, close brackets 2. What this means here is it means we've got 2 hydroxides attached to the 1 calcium. And then we also get the hydrogen gas. Now, when we react a metal and an acid, they react to form a salt and a hydrogen. There'll be something more on naming these salts in a later video. A salt, by the way, in chemistry is not what you put on your fish and chips necessarily, although that is a salt. But a salt is an ionic compound that's formed when a metal reacts with an acid, and you get a metal and a non-metal in an ionic compound. Okay, so that's what a salt is. It's where something reacts with an acid and we get an ionic compound of a metal and a non-metal. And we get a general equation for a metal reacting with an acid, and that is metal plus acid makes a salt plus hydrogen, and you are expected to know that and be able to talk about that. So you'll know if a metal is reacting with an acid because you'll see the bubbles of hydrogen being produced, and then we can do the squeaky pop test to see if that gas really is hydrogen. So the next step, why is hydrogen and carbon on the reactivity series? And there is a very good reason for that, and that's because most metals, when we find them naturally, they are found in rocks called ores. You've probably heard of that word before, O-R-E-S. And what an ore is it's basically a rock that contains a lot of metal, and that you can get the metal out of it. The slightly more complex or more accurate definition is it's a rock that contains a high enough amount of metal to make extraction economical on a commercial scale. So extraction means to take something out, so it's getting the metal out of the rock. If a metal is below hydrogen on the reactivity series, so if it's below hydrogen on the reactivity series, which on the reactivity series we've had a look at contains copper and gold, but you can also put other metals into there as well. If it's below hydrogen, then you can extract the metal from its ore by heating up the ore and passing hydrogen over the ore, and what will happen there is the hydrogen will react with whatever the metal is reacted to, and you'll get your pure metal. If the metal's below carbon, you can then extract it by heating the ore with carbon. Okay, and in fact what you'll generally see is even copper isn't extracted by heating with hydrogen, because hydrogen is explosive, it's a gas, it's quite hard to get hold of, and it's relatively expensive compared to carbon. Carbon is very, very cheap, so they'll extract actually copper from its ore using carbon, because carbon is cheaper than hydrogen, it's easier to manage. Now what this does mean is if you've got something that's between hydrogen and carbon on the reactivity series, and if you remember carbon's slightly above it, you won't be able to extract it with hydrogen, and we'll have a look at that now. Okay, so if we've got iron is below carbon on the reactivity series, so we could extract it from its ore using carbon. Iron though is above hydrogen in the reactivity series, so we cannot extract iron from its ore using hydrogen. The iron will hold on to the stuff that it's attached to in the ore, and the hydrogen won't do anything. Magnesium, calcium, lithium, sodium and potassium, however, you can't extract those by heating them with carbon. They're just too reactive, and these require electricity and a process called electrolysis, which we'll be coming on to at a later lesson. And you need electrolysis to get those from their ores. Now for a displacement reaction, so getting a rock or getting a metal out of its ore in the rock is an example of a displacement reaction, but we're going to look at some of the lab-based ones here. Okay, so a displacement reaction is where a more reactive metal displaces or swaps places with a less reactive one in a compound. So for example, if we have a solution of copper sulfate, that nice blue coloured solution, and we add to it, we drop in some more reactive metal, for example iron or zinc, then the iron will displace the copper and steal the sulfate for itself. Okay, so what happens is we take our iron plus our copper sulfate, and we end up with iron sulfate and copper. You can see the iron and the copper have swapped places before and after the arrow. The iron, we say, has displaced the copper from the sulfate. Okay, so it's taken its place, it's stolen it, it's more reactive, so it walks along up to the copper sulfate and it says to the copper, hey, I want your sulfate, and the copper says, well, I don't want any trouble, and steps to the side, and the iron takes the sulfate and leaves the copper all by itself. And here's the simple equation for that reaction. We got iron is Fe, solid, plus our copper sulfate, CuSO4, SO4 being the sulfate part, in brackets aqueous, and then after the arrow, after the reaction, we get iron sulfate, FeSO4 plus copper solid. Now a less reactive metal cannot displace a more reactive metal, no matter what you do, unless you use electricity. So copper plus iron sulfate, if you were to do that, you've got some iron sulfate in a beaker, you add some copper to it, there won't be a reaction. Nothing will happen at all. Okay, so the iron's too strong, the copper can't steal the sulfate away from it. So, little summary. Some metals are more reactive than others. The reactivity series shows the metals in order of their reactivities, and the reactivity series includes carbon and hydrogen because you can extract metals from their ores with those two things. If a metal reacts with water, it will make a hydroxide and hydrogen. A hydroxide contains OH- on the hydroxide ion. If a metal reacts with an acid, it will make a salt and hydrogen. And lastly, a displacement reaction is where a more reactive metal takes the place of a less reactive metal in a compound. Okay, thank you very much, guys. Well done. Please remember to subscribe, to like, leave any comments. If you are in one of my classes that I am currently teaching, then fantastic. You can ask some more questions in Teams and in the Teams chat, or when we're back in school in lessons. If you as people I have taught previously, hello guys, it's good to see you in the video. Please leave a comment. Be nice to hear from you. It'll be interesting to hear, Scott, if you have decided that a mole is 6.022 times 10 to the 23 yet, or if you still persist with the myth that it is a small furry rodent. So please remember to hit the like and subscribe. And also, if you are new and I've never taught you before, I hope you found this video useful. Again, please remember to like and subscribe and to share the video. It does help the channel, it does help me get the motivation to make some more videos. Okay, thank you very much. Take care, guys. Have a good time.